We are looking at vectors in a plane. At the end of this lesson, we will be able to represent vectors as directed line segments. We will be able to write the component forms for a vector. We will be able to perform basic vector operations and represent vectors graphically. We will be able to write vectors as linear combinations of unit vectors, find the directions, angles of vectors, and use vectors to model and solve real-life problems. So let's get started. First things first, what is a vector? There are plenty of things that we can talk about that are represented by numbers. Think about temperature, or think about weights, or think about distance. Now, distance brings up a unique type of problem for us, though, because sometimes distance matters. It matters when we're measuring distance and what direction we are measuring distance in. So let's take an example here. So let's say I am starting at the origin, and I start at the origin. Let me make my dot a little bit bigger. I'm starting at the origin, and I go 3 miles east. And then I go 4 miles north. Now, if I ask you how far I've traveled, you could say, well, that's easy. 3 plus 4 equals 7. But if I ask you, how far am I from my original starting point, that becomes a different story. Now we got to take into account that old Greek guy that we like to talk about, Pythagoras, and I have to say, well, my distance squared, which is d right there, equals 3 squared plus 4 squared, which equals 9 plus 16, and d squared equals 25, so my distance equals 5. And those are two very different problems. So how far I've traveled and how far away am I from my starting point. Vectors are a mathematical way for us to solve the second type of problem. So let's talk about this. A vector is simply a measure that it measures both magnitude and direction. The first way we're going to show how to represent vectors is via component form. And we'll get into that we'll get to that right now. So, if I have a vector going from the origin to, say, this point right here, which is 4, 5. I just draw a line there. That shows me direction, and it shows me magnitude. The magnitude is my length from the origin. My direction, obviously, is my angle from the positive x-axis. We will learn how to measure it that way as well. But component form simply takes these two numbers, the 4 and the 5, and represents them just like we would represent an ordered pair. However, to show that it's a vector, I use angle brackets like this. So this vector is 4, 5, and then to show that it is a vector, I put them in angle brackets like so. Opportunity to do some math. So let's take that 4, 5 vector. So I got a 4, 5 vector, right? Let's write that down here. 4, 5. And I also want to add another vector to it. Let's say I want to add another vector. Let's go 4, 3. So right there. So I'm going to go 1, 2, 3, 4, and up 3. So 4, 3, like that. Now, this vector is 4, comma 3. Now, it might help us to put this in terms of a word problem. So, let's say my path was the green path, and I walked 4 miles east and then 5 miles north. That gets me to spot 4, 5 in my coordinate plane. And then I walk 4 miles east and 3 miles north. How far have I walked? Well, there's a couple ways that we can do this. Now, I'm going to show you graphically. I go over 4, so 1, 2, 3, 4, and then up 3, 1, 2, 3. And I draw from the from the tail of the one vector to the tip of this new vector, and I misplaced my component form vector, but you'll see the point I'm trying to make here is right here at this point is my new destination. And if I just do some math, I can tell that I've gone 1, 2, 3, 4, 5, 6, 7, 8 over, and 1, 2, 3, 4, 5, 6, 7, 8 up. And so I am now at 8, comma 8. And so simply to add these two vectors, I add them by saying, and here I'm going to introduce you to some notation. Let's call this top vector u. We'll call it top vector u, and this bottom vector, so u equals that, and this bottom vector equals v. And notice the little arrow that I put on top of the vector. That shows you that it's a vector. You will also see it referred to in the textbook when they simply do bold, they make the vector a bold letter. So there'll be a bold-faced U and a bold-faced V without the little arrow on top. But since we're writing and we can't do bold as well with a pencil, we just put that little arrow on top. So now I'm going to show you how to add these. So U plus V equals, and then I'm going to put this in vector brackets, and that's going to be the U is 4, and I'm adding the 4 from the yellow vector, and then comma, and 5 from the green vector, comma, and 3 from the yellow vector. And that is how you add vectors. You just take the x component of one and add it to the x component of the other. Take the y component of one and add it to the y component of the other. And you get your new vector. Same thing goes with subtraction. So, u minus v would equal 4 minus 4, and then a comma, so the x components, and then 5 minus 3. Oops, let's make that a black bracket. And then u minus v equals, and then 4 minus 4 is 0, and 5 minus 3 is 2. Now, you've seen how to subtract vectors. Now you might ask yourself, well, what if I'm not at the origin? How can I do a vector then? Well, it's quite simple, pretty much. Just because I don't start at the origin, I can still have a vector of length 1, 2, 3, 4, 4, and 1, 2, 3, 4, 5. So this vector, even though it starts at, let's see, what is that point? 1, 2, 3, 4, 5, 6, 7. This starts at -7, comma 3. And then it ends at -3, comma 8. Is that right? Yep. So, even though it starts at a different point, this still is vector. This vector is 4, comma 5. It has magnitude and it has length, it has direction. It does not matter that it starts at a different place, it's still the same vector. Okay? So, where does that leave us? Let's scalar multiplication. Let's say I want to take the same guy on the same trip, and he goes 1, 2, 3, 4, 5, 4 over, so 4 units, 4 miles east, and 5 miles north, which puts us right there again. So I tell you, our hero walks 4 miles east and 5 miles north, and he does that 3 times over. Where is he? Well, my u equals 4, comma 5. And now he's walked this 3 times. So 3 times u equals 3 times 4, comma 5, which then gets me, and you can probably guess where this is going to end up, equals 3 times 4, comma 3 times 5. It's not distributing, but you can think of it as distribution. It kind of looks the same, and really we're doing the same thing. So 3u equals 12, comma 15. So if he were to do this trip 4 miles east, 5 miles north from some origin point, and he did that walk 3 times over, he would end up 12 miles east and 15 miles north of his original starting point. And that's what that means. We're going to talk about some properties. We're going to talk about u. Actually, I want black now. I want u, v, and w to be vectors, and c and d are scalars. Now, scalars are simply numbers that have magnitude only. They have no direction. So it's the opposite of a vector. A vector has both magnitude and direction. Scalars have magnitude only. Now, u plus v equals, my vector arrow, v plus u. So we can say that vector addition is commutative. Okay. We can also say u plus v plus W equals U plus V plus W. So we can also say that vector addition is associative. We can also say that vector addition has an additive identity. So U plus the zero vector. Now, the zero vector would be 0, 0. Let's just put that in notes here. 0 equals 0, 0. Okay? We also know that U plus the opposite of U, so plus minus U, put that in parentheses here, also equals the 0 vector. We also know, so let's number these. So this is 1, this is 2, this is 3, this is 4, number 5. Number 5 is C times du is equal to CD times U. And I got to put those arrows on there. I'm getting in the bad habit of not putting my arrows on. Now, this is also associative property, but this one is just the associative property of scalar multipliers. So notice I can multiply my vector times D first here, and then multiply by C, or I can multiply by my scalars before I multiply it by my vector U. Okay? Number 6 is C plus D times my vector U equals CU plus DU. So this is a distributive property. So now, the distributive property is only good when we're multiplying a vector by scalars that are being added together. I cannot distribute, well, we'll get to that later. Let's do the next one. C times U plus V equals, that's an equal sign, that's not a 2, equals CU plus CV. This is also the distributive property, okay? Okay, now, a couple more properties. Now, 1 times my U vector equals U. That is what we call the multiplicative identity. And 0, this is scalar 0, there's no vector arrow above it, times U equals the 0 vector. Notice now I have a vector there. And number 9, last but not least, the absolute value of CV. So this is a constant times V. And now, a little bit different deal here. So these absolute value bars are different between scalars and vectors. So absolute value for a scalar is just like you remember it. And an absolute value for a vector is double bars, okay? So we're multiplying the absolute value of C times this vector in double bars. And what this represents is something different. Let's go to the next page. So U in double brackets, double absolute brackets like that, is the magnitude or length of U. And as you can probably guess, we are going to use the Pythagorean theorem to find the magnitude of U. So that equals the x component of U squared plus the y component of U squared. And then I take the square root of that, and I'm taking the absolute value of the whole thing. I am only interested in the positive square root. Now, what we want to do with this information is we want to be able to find a unit vector in the same direction as my given vector. So let's let U equal that 4, 5. Actually, let's make it 3. Let's make it 4, 3. We're going to cross that out and let U equal 4, 3. And you'll see why I did that in a second. Pardon my bad penmanship. So my magnitude of U equals the square root, well, the absolute value of the square root of 4 squared plus 3 squared. And that equals the square root of 25, right? Because the absolute value of 16 plus 9. And that equals the square root of 25 inside absolute value brackets. And that equals 5. So, my magnitude of U equals 5. Now, if I want to find the unit vector of U in the direction of U, that is going to be, so the unit vector equals, it's going to equal U divided by the magnitude of U. Okay, so this is going to equal 4, 3 divided by 5. And that's going to make our unit vector equal to 4/5, 3/5. Now, let's test our theory. 4/5 squared plus 3/5 squared equals 16/25 plus 9/25, which equals 25/25 equals 1, and the square root of 1 is 1. So we have found our unit vector. So we take our vector that we're given, and we divide it by the magnitude of that vector to find our unit vector in that same direction. Now what I want to do is I want to find the direction angles for vectors. Now, a good way to do that is to think of a vector superimposed on the coordinate plane with the tail of the vector being at the origin. And then we can measure the angle just like we would any angle theta from the positive x-axis. So in this particular case, I'm measuring from the positive x-axis to my vector. So theta is written there in yellow. And, well, how will we do that? Well, I can construct a right triangle, can I not? I can construct a right triangle right here, and I didn't want to do that in yellow. I wanted to do that in black. Do that from here and here. And I got a side of 3 and a side of 3. And I know that my angle has my tangent of theta is opposite over adjacent, so equals 3 over 3. And then to find theta, theta equals simply the inverse tangent of 3 over 3. And so theta equals 45 degrees, or pi over 4 radians. And we choose 45 or pi over 4 based on the fact that we know this is in the first quadrant. Fairly straightforward. Now, where thinking of angles in terms of trig functions is helpful to us is remember that all of our trig functions are represented by a unit circle, which means that any trig ratio also is a unit vector. What does that mean? Well, it means that when I have, let's say I have something that has a sine of 1/2, let's try this again. I have a sine of 1/2. Nah, I didn't want that either. So, I'm sorry, cosine of 1/2 and a sine of root 3 over 2. Okay? And so if I square the first one, I get 1/4. When I square the second one, I get 3/4. 1/4 plus 3/4 is 1. So you'll notice that I chose to do the angle of 60 degrees. Now, 60 degrees is right about here. So we'll put that right. Don't want to put it right there. Put it about right. Let's see if that's 1/2. We'll put it about right there. So that's our vector right there. And that has a unit length of 1. So I can represent the cosine of 60 degrees and sine of 60 degrees as my unit vector, which is pretty handy because now if I'm given an angle, like as in a bearing or a heading, or just an angle from some arbitrary point, I can create a unit vector just by applying sine and cosine to that angle. So how does this work? This fact can be pretty helpful when we're trying to calculate something like airplane speed. So, if an airplane is traveling at 500 miles an hour and at a bearing of 330, so I did it again, give me a second, at a bearing of 330 degrees. And remember, 330 degrees, we always measure bearing from straight north and go clockwise. So 330 degrees in this direction. And just to confuse you, they measure from north and go clockwise instead of starting at the x-axis and going counterclockwise. So 330 degrees is about there. And let's just reach out here. And that was awful. That is my airplane. And it's going 500 miles an hour. And it's going in the direction of 330 degrees. Now, 330 degrees from north, going in the clockwise direction from north, that means this angle right here, and I'll put this in green and I'll make it a little fatter, that means this angle is 30 degrees right here. Add that to 90, right, because that angle is 90 degrees. This angle is 120 degrees. So it's just one of the math gymnastics things that you're going to have to do to convert angles or bearings back and forth. And now that I have this angle, I have a unit vector that I can use to help. And what would that unit vector be? Well, remember, it's cosine of 120, comma, sine of 120. And that is my unit vector. So now I know the magnitude, which is 500 miles an hour, and it's going in this direction. However, there's a side wind. And that side wind is coming at a 45-degree angle. So the wind is going it's going northeast. So northeast is, and I wish I had another color, but I'll use yellow. The wind is going this direction, northeast, which is, the unit vector there is cosine of 45 degrees, comma, sine of 45 degrees. Okay, and that wind is going at a velocity of 70 miles an hour. So my wind is at 70 times cosine of 45, sine of 45 degrees. There we go. Now, it asks me, what is the resultant speed and direction of the airplane? So what it's asking you is, the wind is going to blow this plane a little bit that way, because that's the way the wind's going. How far is it going to blow it in that direction? Or, more importantly, what's the new speed and heading going to be of the airplane? So, what we have to do is we have to add our bearing of the plane to our wind. So, quite simply, I take 500 times the cosine of 120 degrees. That becomes negative 250. And take 500 times the sine of 120, which makes it positive 250 root 3. And then I add it to 70 times the cosine of 45, so that would be 35 root 2. Actually, that would, that's positive, and multiply it times the sine of 45, which is also going to be 35 root 2. And just so you know, I got that by multiplying 70 times the cosine of 45. Remember, cosine of 45 is root 2 over 2. 70 times root 2 over 2. 70 simplifies with the 2 in the denominator. It becomes 35. And I'm left with the root 2. So now I'm adding these two vectors together. And remember, when I'm adding these two vectors, I add x component to x component and y component to y component. And I get, and this is going to be a mouthful, but I'm going to get 35 root 2 minus 250, that's my x, and 35 root 2 plus 250 root 3. And I ran out of room there. That's 250 times the square root of 3. And that is your new vector. That is what the direction and the speed of the airplane. Well, we say speed. Let's find the speed. Let's find a number for that speed. Well, I have to square 35 root 2 minus 250. So that squared is, let's see now, what is that? Well, that would be, let's figure this out. So 35 root 2 minus 250 is going to be roughly 200.5, and that's going to be negative. And then comma, 482.5, and that's my y. So now that I have the x component and the y component, I can simply use Pythagorean theorem and square the two and come up with a speed. And the speed is going to be, well, 200.5 squared plus 482.5 squared. And take the square root of that, I get 522.5 miles per hour. And there you have it.